Welcome to part 3 of the third module of MOOC, RTS and Hardware-in-the-Loop Validation of Modern Energy Systems. This presentation focuses on the validation of modern energy systems through geographically distributed real-time simulations. I am Mazher Syed. I'm a lecturer at the University of Strathclyde, and I will take you through the complexities and innovations in this field. The outline sets the stage for our discussion. We will first discuss the transformation of the grid, the challenges it presents, and the potential ways to tackle the transformation. I will then introduce the concept of geographically distributed simulations, followed by the taxonomy we have developed. We will then explore the current developments in the field and conclude with insights that will help us understand the future landscape of energy systems. As is widely recognized, power systems globally are undergoing a major transformation due to the large-scale integration of renewable energy sources. Operating a future grid dominated by renewables and characterized by low inertia present considerable challenges. While we often speak of these issues as future concerns, they are already becoming evident. For example, the power outage in Britain in August 2019 is a case in point. This event highlighted the urgent need for adaptive operational strategies to manage the growing complexity and variability of modern energy systems. Addressing the transformation of the power grid effectively requires the adoption of innovative technologies. However, these technologies must undergo rigorous validation before being deployed. A structured validation process must be followed, progressing from pure simulations to controller hardware-in-the-loop simulations, then to combined controller hardware-in-the-loop and power hardware-in-the-loop simulations, and in the end, finally, a field trial. This stepwise approach is designed to increase the technology readiness level and is essential to ensure that new solutions can be integrated into existing systems safely and reliably. While validation is essential, a major challenge lies in the growing complexity of modern energy systems, which demands highly detailed and precise modeling. The integration of sectors such as heat and transport further compound this complexity. These advancements require substantial computational resources, specialized tools, and expert knowledge. Additionally, concerns around intellectual property protection remain a persistent issue throughout the process. Geographically distributed simulations offer a powerful solution in this context. By linking laboratories across different locations via the internet, these simulations enable collaborative experiments that draw on the unique strengths of each facility. This approach significantly enhances research and development, allowing for more robust and wide-ranging testing and validation of energy systems. Here are some of the perceived advantages of geographically distributed simulations. They include comprehensive characterization of energy systems. Leveraging multiple laboratories allows for large-scale and detailed network modeling, which can be utilized to undertake more representative analysis of complex energy scenarios. Beyond enabling detailed system characterization, geographically distributed simulations also streamline the validation process. By drawing on the specialized expertise of different laboratories, this collaborative approach enhances efficiency while maintaining intellectual property protection, since models remain local and do not need to be shared. Geographically distributed simulation techniques can be broadly categorized into three main types. First, geographically distributed real-time simulations, which is the linking of real-time digital simulation platforms across multiple locations. The second one is geographically distributed controller hardware in the loop, GDCHIL, which is the integration of remote physical controllers with simulated environments. And finally, geographically distributed power hardware in the loop, which is GDPHIL, which extends the CHIL by incorporating real power hardware across these sites. This taxonomy helps us to guide the selection of appropriate GDS techniques based on research objectives and system requirements. Next, we will walk through practical examples of each of these categories to illustrate their applications and benefits. The first example illustrates the application of GTRTS in validating frequency control strategies across a split power network between Dynamic Power Systems Laboratory and the Power Networks Demonstration Center located 21 kilometers apart. Leveraging geographically distributed simulation, the setup enabled a proof of concept evaluation using real-time simulators connected over the internet. Key highlights include the demonstration of the feasibility of use of geographically distributed simulations for dynamic studies. Also, it served as a demonstration of system robustness under communication delays. Finally, validation of inertial response using swing equation-based control scheme, which gives us the confidence then in validating any other slower frequency control mechanism. The second example showcases the use of GDCHIL for validating frequency and voltage control strategies in a microgrid. The setup involved a power network which was located in Singapore with controllers operating remotely from the UK and France, spanning a distance of over 11,000 kilometers. Key aspects include the proof of concept validation of distributed control across continents, use of GDCHIL for dynamic performance studies under realistic conditions, integration of remote laboratory expertise to enhance system levels testing. Furthermore, the results demonstrated stability in both frequency and voltage profiles within the microgrid. This case highlights how geographically distributed hardware-in-the-loop setups can support advanced control validation while leveraging global collaboration without compromising any intellectual property or requiring physical co-location of assets. Final example demonstrates the use of GDPHIL, including CHIL, to validate voltage control strategies in a distributed network that was spanned across 5 countries, covering distances of up to 1,780 kilometers. The setup integrates real hardware components across multiple labs. We had a photovoltaic system at RSC in Italy, a battery system at DTU in Denmark, and a controllable load at VTT in Finland. A central voltage controller was hosted at the University of Strathclyde. The key takeaways from this example are that this served as a proof of concept validation of voltage control using centralized voltage control CVC, the seamless integration of geographically dispersed hardware assets, and interactions capturing the real-time interactions between CHIL and PHIL environments. This case highlights the potential of GDPHIL to support cross-border collaboration, enabling realistic and scalable testing of advanced control schemes. While GDS has demonstrated strong potential through successful proof of concept projects, its widespread adoption still faces several challenges. These key challenges include ensuring secure data exchange, maintaining the robustness of distributed setups, and improving the accessibility across diverse research environments. To address these barriers, the ERIGRID 2 project was launched under the EU Horizon 2020 program. This initiative brings together 20 partners from 13 countries operating 21 smart grid laboratories. ERIGRID 2 is focused on developing advanced testing methods, tools, and services to support the validation of smart integrated energy systems. By fostering collaboration and standardization, the project aims to make geographically distributed simulations more scalable, secure, and accessible for broader energy research community. The challenges that hinder the widespread adoption of the techniques include complexities in setting up reliable communication links between labs, security concerns, particularly from industrial stakeholders, latency issues that arise over long-distance connections. To address these, ERIGRID 2 project is actively exploring cloud-based interconnection of laboratories. This approach aims to simplify integration, enhance security, and mitigate latency through optimized routing and infrastructure. The graphs on the right illustrate early proof of concept results comparing time delays across different sampling frequencies using Amazon Web Services, and other cloud platforms. These results demonstrate the feasibility of maintaining stable performance even under geographically distributed conditions. Now, in terms of realizing robust setups, several challenges still remain. The current stability analysis methods often fall short, particularly when applied to dynamic and geographically dispersed systems. Most existing techniques rely on static impedance ratios, which are insufficient for capturing the complexities. To address these limitations, ERIGRID 2 project is exploring advanced solutions, including development of detailed stability models that better reflect the dynamic behavior of the systems, adaptive Smith predictor compensator to mitigate the effects of communication delays, and virtual shifting impedance techniques to enhance the system resilience and flexibility. These innovations aim to establish a more reliable foundation for GDS, enabling broader adoption and more complex experimental configurations. This slide talks a little bit more about the detailed stability models that were developed. Here we present some sample results that show how the model performs in different conditions, such as varying time delays, the line resistances, and the power factors, and provides strong evidence of the effectiveness in enabling robust and reliable setups. While geographically distributed simulations offer powerful capabilities, they remain difficult to use at large scale. Inconsistent protocols and data formats across different laboratories, challenges in maintaining reliable data transmission rates, and the complex initialization procedures when coordinating multiple laboratories. To address these challenges, ERIGRID 2 introduces the Research Infrastructure as Code framework, the RIASC framework, which is a unified programmable approach designed to simplify and accelerate the setup of geographically distributed simulation experiments. RIASC enables seamless orchestration across software, hardware, and infrastructure layers, making advanced testing more accessible, repeatable, and scalable. Then we come to our concluding remarks. Geographically distributed simulation presents a promising pathway to tackle the increasing complexity of modern power systems as they transition towards higher share of renewable energy. While several proof of concept demonstrations have validated its potential, widespread adoption still faces technical and operational challenges. To move from concept to practice, continued collaboration is essential. Initiatives like the ERIGRID 2 Laboratory Access Program and the IEA ISGAN-SURFAN Advanced Laboratory Testing Methods task are playing a key role in advancing methodologies, fostering innovation, and building a more connected and resilient energy research ecosystem. Thank you for your attention. If you have any questions or would like to discuss the topics covered further, please feel free to reach out to me at the University of Strathclyde. I'm looking forward to engaging with you on these important developments in the energy systems.